Hi guys, and welcome to Unit 6.1 Notes. We're going to talk about kinetic theory in gases. Please feel free to pause this video as you need to. So say I go too fast. Well, the nice thing is unlike in the classroom where you don't have a pause button, you can pause this and you can catch up as you need to. So feel free to use that feature. All right, so in 6.1, we're going to begin by introducing what kinetic theory is and then talk about some of the factors of gases, particularly focusing on gas pressure. So what is kinetic theory? Well, kinetic theory is the model that attempts to explain the behavior of gases. In this unit, we're going to be looking at how does changing temperature affect the pressure of gas, how does changing volume affect gas, and all that comes down to is understanding that this is focusing on the little particles of gas that are in a container. So what we need to remember is that all types of matter have particles that are in motion. You remember from way back at the beginning of the year, we talked about the particles in solids, liquids, and gases. And remember in solids, the particles are really close together, but they're vibrating. And they're still moving, but they're so tightly packed that it appears as if they're not moving. Compared to liquids, where they're a little further apart and they are moving and they can flow, hence why liquids have fluidity. And then our gases were way far apart, and there's a bunch of them, and they're moving all over the place. Okay, so we're going to be focusing on those particles that are moving all over the place here. But before we get into that, we have to understand that as particles are moving, they're going to have energy. And so we're going to be looking at different types of energy today. So we're going to review. We're going to go back to your integrated science days. And we're going to talk about kinetic energy versus potential energy. So Ke, you'll remember, is kinetic energy, and that is energy in motion. It's energy doing an object that is moving. So think of some of these examples like the ball or rock rolling down a hill, or say water flowing over a dam or over a waterfall, or riding the actual bike or swinging a bat or golf club. These are all examples of energy in motion, which would be an example of kinetic. So in our gases, they're constantly moving. They're going to have a lot of kinetic energy. And we'll talk about that some more because we're going to find out that there's a relationship between kinetic energy and temperature later on in 6.3. So the second type of energy is PE, which you should remember is potential energy. And potential energy is stored energy or energy due to position or composition. So this is energy that an object has, but it's not moving, but it has the potential to do energy. So this would be like the wind-up of a golf swing or about to hit a bat. It has the potential to move, but it's not yet. It's storing that energy. Going back to our rock and water examples, that would be like a rock on top of a hill versus the water behind a dam. Both of these, they're not moving, but they have the potential to do that. And what we know about energy is that it can convert from one form to another. So potential energy, if you then push the rock, it's going to go from having potential to having kinetic, just like this marker right now. This marker, I'm holding it up. It has the potential to move. So it has potential energy. When I let it go, that movement is kinetic energy. And then it hit the table and it's not moving again. So it goes from potential to kinetic back to potential. And so we see that throughout all of these things that there is always this conversion of energy from one form to another. And that's because energy has to obey what we call the law of conservation of energy. We've seen many of these laws so far. We've seen the law of conservation of mass. We've seen the law of conservation of matter. And what we remember from those is, remember, what you have in the beginning, you have to have at the end, even though it may look different. So we did balanced equations. Remember that if you had 6 hydrogen at the beginning, you had to have 6 at the end, even though it might be bonded with something new. Well, the law of conservation of energy does the same thing. The law of conservation of energy tells us that energy can be neither created or destroyed. It just changes from one form to another, just like potential to kinetic back to potential. Sometimes we'll see kinetic energy, we'll get back to potential, and sometimes it's like, but it stops. Well, that's because energy is transformed into other forms, such as light or heat, and sometimes we see that in our chemical reactions. So we're seeing it's not like the energy just disappeared, it just turned into another form. So this helps us understand a lot of what's going on with our gas particles. So the second main focus of today's lecture is talking about pressure. We're going to be looking at gas pressure. So the question is what's gas pressure? Well, gas pressure is the collision of all those billions of gas particles in an object. So remember, inside our container, we have a whole bunch of gas particles, and they're all moving around, and they're bound to run into each other. And the more they run into each other, the greater the gas pressure would be. So think, for example, if we had an empty balloon, we know that it's not truly empty. It has just very little of gas particles. So very few gas particles, your chance of running into each other is very slim. But you start to blow up the balloon, you're putting more and more and more particles into that, and you're going to run into each other. Just like in my house right now, if I tried to fit 1,000 of us in here, which we wouldn't want to do right now, obviously, but if we had 1,000 of us in here, we would more likely run into each other. Versus the 3 I have in my house right now, I can send one of them downstairs, one across the room, across the house, and I'm less likely to run into them. So the more and more particles you put into a container, the more likely they are to bounce into each other, which increases the pressure. And as you know, that pressure keeps increasing. Eventually the container it is in could burst. So what happens if you have something that has no particles present? Think about outer space. Outer space, there is no gas, no atmosphere. It's pure emptiness. And we refer to that as a vacuum. And sometimes it's cool to create vacuums so that we can study how things act in perfect conditions. So do we experience gas pressure? Does it affect our everyday life? And the answer is yes, it does. We are surrounded by gases. Our atmosphere is created of lots of gases: nitrogen, oxygen, carbon dioxide, water vapor, and all of them are exerting pressure on us. And how are they doing that? Thanks to gravity. Gravity, remember, gravity is going to act on anything that has mass. Well, these air particles, these gas particles have mass, not a ton of mass, but they have mass. So gravity is exerting a force and pushing them down. And so they are exerting pressure on us. And we call that atmospheric pressure. And so this simply results from all of the collisions of the air molecules. Remember, they're being pushed down. So they're being pushed down, they're being forced into a smaller space. So more particles, smaller space, more collisions. So think about that. We'll talk about in a minute. Altitude can affect that. And so you might want to ask yourself, well, why don't we feel that atmospheric pressure? Well, I will tell you that there is a video that you're going to watch, about a 3-minute TED Talk, and it's going to explain to you why we don't feel that massive pressure on us. Like, why aren't we being crushed like hands because of that pressure? Whereas if you were to go like to Venus and step off of Venus, there's so much gas pressure there that it would crush, you would literally just melt your bones. So why don't we feel that here? And that video will kind of explain that we're doing something back to the gases. So atmospheric pressure varies. You'll see in your notes weather. We'll talk about weather later, so we're going to skip that part. But I do want to talk about altitude. At sea level, you're going to have the most maximum pressure. So think about it. We're pressing down. Where is that pressure going to feel greater? At the bottom. So at sea level, that's what we're going to call standard pressure, is where you have the highest gas or atmospheric pressure on Earth. The higher you go up, the less you feel it. And so in higher elevations, there's less air pushing down on the Earth's surface. So that's why they say the air is thinner at higher altitudes. And that's why people who go mountain climbing and things like that have to be careful and let their bodies adjust, because if they don't get as much oxygen consumption and can have blackouts and other things like that. So higher elevation, lower pressure. We're going to always start with standard pressure at sea level. The maximum the pressure is right here. So all of our pressure calculations are always based off of comparing to what it is at sea level. And that's that video that you'll watch later that's on Canvas. So how do we measure atmospheric pressure? How do we know this number that we get? If you ever watch the Weather Channel or anything like that, you'll hear your meteorologist mention the air pressure is this number. Well, how do we get that number? Well, we use a tool called a barometer. And it's simply a device that measures atmospheric pressure. And it was invented in 1643 by Torricelli, who was a student of Galileo. What he did was he took a glass tube of mercury and he stuck it into a bowl of mercury, and he wanted to see how it would fall. And what he found was it actually stayed in place for the most part. And that's because that pressure was keeping it there. And so he actually found that it rose or stayed at a level of 760 millimeters of mercury, which is going to end up being our standard unit of pressure we'll talk about here in a minute. So as far as units go, there are 3 units of pressure, just like we have miles, inches, and feet. We use mmHgs, which is the height of mercury in millimeters from Torricelli's invention, atmospheres, and kilopascals. Now, for what you need to really focus on today is our standard units of pressure. What is that number at sea level? Well, that's this conversion right here. 1 atmosphere, this is all at sea level, standard pressure is 1 atmosphere equals 760 millimeters mercury equals 101.325 kilopascals. What this allows us to do then is to convert between units. It's like saying 12 inches equals a foot. So now you can convert between things. Well, we're going to use this to convert. So if you look in your notes, we have a few practice conversions that we are going to do. So I'm going to stop sharing for a minute. And I'm going to bring out my whiteboard. I'm sorry that there's a little bit of a glare. I'll do my best here with this. So I'm going to scoot over here, show you my board. All right, so at the top, which is your number 1 on the conversions, is our simple units of pressure, standard pressure conversion. 1 atmosphere equals 760 millimeters of mercury equals 101.325 kilopascals. These are the conversion factors we are going to use. All right, so then number 2 is how many atmospheres. So 2.1 atmospheres is how many millimeters mercury. So we're going to use our factor labeling here. And I'm going to do all of our steps. If I can get the thing off right. All right, so when we factor label, we're going to remember that we're going to start by putting what we know up here. And then I'm going to put the conversion factor. Remember, whatever I put up here, I have to put down here. So I'm going to put 1 atmosphere. And I'm going to put up here where I want to go, millimeters mercury. So I'm going to put here 760. And remember, across the top, we multiply. So I'm just going to need to multiply those 2 numbers. And when I do that, I get 1,596. All right, so let's look at the next one. Let's reverse it now and go from millimeters mercury to atmospheres. So I have 798 millimeters of mercury. I want to know how many atmospheres that is. So I'm going to start first by putting what I know right here. And I want to go to atmospheres. So down here, I have to put what I have up here. So I'm going to put 760. And how much atmospheres is 760? 1. So if you remember, when doing this, we divide. When it's on the bottom, we divide. So I'm going to take 798 divided by 760, and I get 1.05. All right, let's do a couple more. All right, so the next one says that I have 750 millimeters of mercury. And I want to find out how many kilopascals I have. So I'm going to make my little factor labeling thing here. And actually, I'm going to do this one down here. That way it avoids that glare maybe. All right, so I put what I know right here. is what I'm given, 750 mmHg. Now remember, mmHg has to go down here so I can cross them out. So, and I want to get to kilopascals. So I'm going to look up here. How many mmHgs do I have? 760. So I'm going to put that down here. And how much does that equal? Kilopascals? 101.325. Now when I go to enter in my calculator, remember I'm going to multiply these two. I'm going to take 750 times 101.325. And then I'm going to divide that by 760. Make sure you're pressing enter on your calculator so things are done right. And you'll get something like 99.99, so we'll just call that 100. All right, let's do one more. So I have 0.8 atmospheres, and I want to get that into mmHg. All right, so what I'm going to do is I'm going to set up my factor label. I'm going to start with what I know, 0.8 atmospheres. I want to get to mmHg, and atmospheres has to go down here so I can cancel them. So I'm going to look up here. 1 atmosphere equals 760 mmHg. So what I'm going to do is I'm going to multiply these two, and I'm going to get 608. All right, you do the last two, so just take a minute, pause the video, and work on the last two. All right, so let's go back and let's talk about the assignments that you have for today. Here in a minute, I'm going to discuss 6.1, and we'll do a couple of extra practices there and kind of talk through it. And then you have a CK12, factors that affect pressure reading and practice. I did make a very short 2-minute video for you to watch on that. So if you go under the assignments, it'll kind of show you, but you'll need to go to your ck12.org account, log in. You should see that factors that affect pressure have already been assigned to you. There'll be a little bit of a reading and a practice to do, but watch that 2-minute video. It really shows you what you need to do there. For Maroon Day, that'll be due April 9th by 11 p.m. For Gold Day, that will be due for you April 14th at 11 p.m. All right, so let's talk practice 6.1. So 8 questions, very straightforward, pretty easy questions here. I'll do a couple of them with you here. First question, number 1. It says, identify each type of energy as either kinetic or potential. So all you really need to do is ask yourself, is it moving? Then it's kinetic. Or is it not moving? Then it's potential. So the first two we did from today, A was water flowing over a dam. So ask yourself, water flowing over a dam, is it moving? And the answer is yes. So that would be kinetic. B says rocks on a mountain. So just think about the rocks on the mountain. Did I say they're moving? No. So we would say that that would be potential energy. Okay, you guys do C and D. Question number 2 is, would you expect particles to have greater motion in a gas or solid? So this says, in which one are the particles moving faster? In a gas or in a solid? We talked about that earlier in the video. Number 3, if the concentration, meaning the amount of oxygen molecules was increased in a container, meaning I'm going to put more oxygen molecules into a container, would the number of collisions increase or decrease? And then number 4, what instrument measures air pressure? So measures air pressure. And then there are 4 more of those conversion ones. I'm going to do 2 of them with you real quick, and then I'm going to let you get onto your assignments for the day. So in practice 6.1, let's look at number 5. Number 5 says 1520 mmHg equals how many atmospheres? Okay, so set up our factor label. Make sure we write what we know here. What I want to get to goes here. So this right here, what I want to get to And then what's up here has to go here. So I'm going to look up here. 1 atmosphere equals 760 mmHg. All right, so remember, multiply across the top, divide by the bottom. So I'm going to divide 1520 by 760, and I'm going to get 2. All right, and then let's look at number 7. Number 7, pretty straightforward. Number 7 says 1 atmosphere equals how many kilopascals? Well, this one we don't even have to do any math. You just got to look up here. So 1 atmosphere equals 101.325 kilopascals. So you need to finish practice 6.1. Remember, there will be a quiz over 6.1 and 6.2 that will be open note and open practice, so it's to your advantage to do those. And work on your CK12. All right, guys, talk to you soon.